Hey there. Here's an overview of what we did out of 6.3 looking at step functions. And we started out looking at what the step function is, which u of t, h of t is 0 when t is less than 0, and it's 1 when t is greater than 0. And we can take that function and shift it so that it stays 0 until it hits some point c there. So we're actually shifting it by a t minus c. And we said it's also equal to what's called the Heaviside function. So there's two notations for it. One using the shifted unit step function, which is this u of c of t, and also the Heaviside function, which just does a shift of t minus c here. And we said the graph of that then looks like a constant function 0 until it hits c, and then it jumps up and goes to 1 from c to infinity. And we also said if you do 1 minus u of c of t, then it's kind of the flip of that. It stays 1 until it hits c, and when it hits c, this piece becomes 1, and obviously 1 minus 1 is back down to 0. So it's just kind of flipped it in a sense. And if we graph u sub 2 of t and u sub 5 of t, both functions are 0 until it hits 2. So 0 minus 0 is 0 to here. Now when it hits 2, just this first function is equal to 1. U sub 5 is still going to be 0. So 1 minus 0 is 1, all the way up until we hit 5. And from 5 on out, now both functions are 1, and obviously 1 minus 1 is back down to 0. So we said you can kind of think of this expression of u sub 2 minus u sub 5 as at 2, it turns on up to 1, and at 5 it turns off, comes back down to 0. If we want to think about the Laplace transform of this before we start using it to graph, we can set up the Laplace transform the normal way we always do for Laplace transforms, in that let's set it up as the Laplace transform is e to the negative st times u sub c of t. But we know that this u sub c of t is 0 until you hit c, which means we can rewrite our integral to be from c to infinity and just remove that unit step function from the inside of the integral. Now we can just simply integrate this function, and we get negative e to the negative st divided by negative s, evaluated from c to infinity. And we can see that it's just simply e to the negative sc divided by s. So kind of nice that when we see this e to the negative sc expression in a Laplace transform, we should recognize that, oh, it comes from a unit step function on it there. So before we do that, let's do another graph using the unit step function. And it's this piecewise function right here. So it's 0 for t's less than 2. And then between 2 and 4, it's going to be this cosine function. And then it's also 0 from t greater than or equal to 4. So it's like saying it turns on the cosine function. Actually, I think in the notes we did a sine function. So let me change that here. This is actually a sine function from the notes. I changed it before class. And then it turns on the sine function at 2 and then turns it off at 4. So we said it should look something like this here. It's 0 until you hit 2, then a sine function that's shifted up until 4, and then it drops back down to 0. And using Sage Math, we saw that, yep, that's exactly what it does look like right here. There. Now, from here, we took a look at the Laplace of a discontinuous function. And this, we ran through a little proof of it here, which said that if you have the unit step function times a shifted function, and that shift, remember, has to be exactly the same as that unit step, then it's simply just e to the negative cs. This comes from the shift and from the unit step. And then it's multiplied by the Laplace of the function. And when we think of the Laplace of the function, kind of think of it as removing this shift, and it's just really the Laplace of f, not f of t minus c. So the first one we looked at was example 4, where we have our function is 0 until we hit 1, and then it turns on, and it turns on this parabola forever. So from t to infinity there. So I can see that since it turns on at 1, we're going to have a unit step at 1, so u sub 1 of t. But then all of these variables in my function here need to also be shifted as a t minus 1. And to accomplish that, this was fairly simple in that here I have my unit step function times the parabola. But if I complete the square on the t minus 2t, or just write it as t squared minus 2t plus 1, that's a perfect square of t minus 1 squared. But since I have plus 2 in my original function, I need to add another plus 1 right here. So my unit step function times t minus 1 quantity squared has the same shift now as my unit step function, and then plus 1. So using our theorem to find the Laplace, it was just e to the negative 1s, that was from the shift, or the unit step and the shift. And then think of this t minus 1 squared as really just a t squared, so it would be 2 over s cubed, plus the Laplace of a constant is just 1 over s. And we verified that that was what SageMath would also give us right on here. There. The next function we took a look at was example 5, which again, here I can see that we've got a unit step of 3, so my function needs to be shifted as a t minus 3. And we saw that that was fairly easy in this instance, because if we factor out a 4, we do get that t minus 3. And so our Laplace will be e to the negative 3s, so that's from our unit step sub 3 and our t minus 3 shift. And then the Laplace of a cosine is simply s divided by s squared plus this 4 squared, 16. And so again, notice that we ignored the step, and we really just thought of the Laplace of the cosine of 4t. And in the proof, that was actually 4 times tau, but dummy variable, we could call it still 4t. And so that's where that Laplace comes from to give us right there. The next one we did not get to in class, and it's a little trickier to find the Laplace of just u sub 2, so a unit step of 2, which means we need a shift of 2, times t squared. And it looks fairly simple to find the Laplace of u sub 2t squared, but remember, we need to get this t squared to look like a t minus 2 squared, and then plus, if there's other terms, also t minus 2. And there's two ways to do it. One is kind of just the guess and check, in that I know it's a parabola, so I know it's going to have a t minus 2 squared. If I multiply this t minus 2 squared out, I get really t squared minus 4t plus 4. And in my function, in f, I just have a t squared. I don't have this other garbage here. So I need to subtract or add 4t, and I need to subtract 4 to make it just be t squared. So on the left-hand side, if I take my guess of t minus 2 quantity squared, add the 4, add the negative 4, that's still equal to t squared. But here I have another problem. This t right here also needs to look like t minus 2. So I'll replace the t with a t minus 2, but now I can see that if I multiply back through by 4, I'm really going to get a negative 8 right here. I don't want a negative 8, so I'm going to add 4 more to it so that I get negative 4, which is what I can see right here is what I need. So my actual function, t squared, written as a t minus 2, is t minus 2 quantity squared plus 4 times t minus 2 plus 4. So that was, sometimes that's easy, sometimes that's tricky to get your function in that form by guessing and checking. Another way to do it is simply just find a Taylor polynomial that's centered at c equals 2. So we can do that by writing down what the function is, what the first derivative, second derivative, and third derivative is. evaluate that all at t minus 2. So it would be 2 squared is 4, 2 times 2 is 4. The second derivative is just a constant 2. And finally, the third derivative is 0, so we don't really need that. So putting it into our Taylor formula, we get y of 2. Get this a little bit bigger for us. Plus y prime of 2, t minus 2, plus y double prime of 2, t minus 2 squared over 2 factorial. And substituting in our values, we see that we get exactly the same expression. T squared can be written as t minus 2 quantity squared plus 4 times t minus 2 plus 4. So that's what we'll take our Laplace of after multiplying it by the unit step function. So here we have our function now written as u sub 2 multiplied by t squared, written as a translated t squared to the right by 2. So we'll have our Laplace is e to the negative 2s from our unit step and from our shift. And then 2 times, think of this as just really a t squared. So that would be s, or 2 over s cubed. This is really 4 times t, so 4 over s squared. And then plus the Laplace of a constant is 4 over s right there. And just to double check it with Sage Math to see how that t squared is handled in Sage Math, it does exactly what we got. It just for some reason factored out a 2 here. So it still got a 4 over s squared, 2 over s cubed, all multiplied by that e to the negative 2s there. So there's how we can take the Laplace of a unit step times a function. What we want to be able to do now is go backwards. So on example 7 and 8, again, we didn't get to these in class, but we want to do the reverse now, is that suppose we do have an inverse Laplace transform that has some kind of an exponential term in the numerator. That tells me that there's a shift of 2 and also a unit step of 2. So we'll have some kind of a u sub 2 of t for our unit step, which means what I really need to do is figure out simply what the 1 over s squared plus s minus 2 fraction is. So kind of think of it as factor out that e to the negative 2s, put it in front. We just need to figure out the partial fraction for the 1 over s squared plus s minus 2. So that's what I did on the left-hand side here. So here's my partial fraction decomposition. It looks like when I split it apart, a was a negative 1/3 and b was a positive 1/3. So my function now is e to the negative 2s times the partial fraction that I just created. And so what that tells me is, well, the inverse Laplace, oops, I forgot my inverse notation here, so let's add in an inverse Laplace on that. That's going to give me a u sub 2 from our shift there and our unit step. Then it'll be a negative 1/3. This 1 plus s over, or 1 over s plus 2, that comes from an e to the negative 2t, but wait a second, it's just not e to the negative 2t. I need my t's to also be shifted by that t minus 2. So it's e to the negative 2 times t minus 2. Same thing with the 1/3 times this 1 over s minus 1 comes from an e to the t. Oh, but wait a minute. Again, we need our shift of t minus 2. So notice that whenever we do the inverse Laplace, we're always going to have a t minus the shift, or in this case, t minus 2 to correspond with our unit step function there. So that's the important part, is make sure you get that shift in there. So let's do one more here, and maybe the challenge problem is let's find the inverse Laplace of e to the negative 3s divided by s times s squared plus 4. And on this one, I can see that we need to have a unit step of 3 from our e to the negative 3s. And so kind of peel that away and just think about trying to find the partial fraction decomposition for the other part of that function, 1 over s times s squared plus 4. So when we do that on the left-hand side, it turns out that a is a quarter, so I'll have a quarter over s. B is negative a quarter, so a negative a quarter times s. And c just turns out to be 0, which is really nice there. So to find the inverse Laplace of these, and again, I forgot my inverse notation. There we are. The inverse Laplace of our fraction will be, well, think of it as taking the e to the negative 3s kind of out of the fraction. Our partial fraction decomposition is 1 quarter times 1 over s minus a quarter s times s squared plus 4. So finally, I can see that we'll have the inverse Laplace of e to the negative 3s will produce our unit step function of u sub 3 of t times, let's see, this first piece is just a quarter. It's a constant, so that just goes to a quarter. And then the second piece is minus a quarter times s over s squared plus 4. We recognize that as a cosine of 2t. Oh, but wait a second. It's not cosine of 2t. It's cosine of 2 times t minus 3. So again, getting that shift in there from our unit step and having the shift needing to be the same as our unit step there. So there's how we can find the inverse Laplace of these expressions that have a negative exponential in the numerator, which corresponds to that unit step. Now, a tricky one is the little challenge problem at the very end here, where we had, if we had to find the Laplace of u sub 4 times sine of t, so that's like saying, let's have it equal 0 until we hit t is equal to 4, and then turn on the sine function without that shift. So notice there's no shift in here, which means we need to create a t minus 4 for here. So if I scroll down to page 5, let's see, where's that at? And we'll do this other one stuff in a different video. But here's the challenge problem. So if I want to take the Laplace of u sub 4 of t times sine of t, I need that sine of t to be a t minus 4. So it needs to look like a sine of t minus 4, which means I'm going to have to kind of have a plus 4 fudge factor here so that inside the sine I still have t, but it's written as a t minus 4 and then plus 4. So in order to find the Laplace of this, let's use our sine sum formula, which remember from trig, sine of the first angle times cosine of the second plus cosine of the first angle times sine of the second. And these two terms, the cosine of 4 and the sine of 4, is simply just a constant. So let's pull that constant out, the cosine of 4 from here. And then when we take the Laplace, we can see that, well, the u sub 4 of t will be e to the negative 4s times a constant cosine of 4 times whatever the Laplace of sine of t is. So again, think of it without the shift. Sine of t is 1 over s squared plus 1. Same thing with our second term. Sine of 4 is a constant. Pull that out. And the Laplace of cosine of t is s over s squared plus 1. So rewriting it with the common denominator of s squared plus 1 and pulling up the constant cosine and sine, we can write the Laplace of that as e to the negative 4s times cosine of 4 plus s times the sine of 4 over s squared plus 1. So hopefully that'll help figuring out how to do the Laplace and the inverse Laplace when we have a unit step function in our expression there. So on the next video, we'll take a look at how to take the Laplace and inverse Laplace if we have a function that is periodic. So stay tuned for the next one.